Okay, guys, here we are at the home stretch for Chapter 6. Let's answer this clicker question. What is the valence shell? You remember the valence shell is the outermost shell. That's where the chemistry happens. Chemistry happens in the electrons that are furthest away from the nucleus. Those are the ones that are most weakly held. If it's a metal, it tends to give up an electron. If it's a non-metal, there tends to be a space available in the valence shell where an electron or two or three can come in and join that valence shell. So the valence shell is the outermost shell. Here we go. For a phosphorus atom, and how many valence electrons does an atom of phosphorus have? Hence, the valence shell is the highest in-principle quantum number. So that's all you're looking for in the valence shell. You're looking for the highest in value, and then to find the number of valence electrons, how many valence electrons for that particular atom, just look at the top of the group. We're looking at phosphorus over here. All we have to do is go over to the left. These are the n-principal quantum values. They tell you about the valence shell. So the valence shell for phosphorus, and remember these n values go all the way across. This is a 2p, this is a 3p. Down here you've got 4p and 5p and 6p, etc., because this is the p block. But it's this value that is telling you what the valence shell. It's the highest in-principle quantum value for phosphorus. To determine the number of valence electrons, just look at the top of the group. This is the number of valence electrons. There are 2 valence electrons in the 3s subshell, so there's 2 over there, and then there's another 3 in the 3p, but they're all at n equals 3, so that's 2 plus 3, that's 5, but all you really have to do is look at the top of the group to find the number of valence electrons. And so the answer to our question is C, because we know that the highest in-principle quantum value for phosphorus is n equals 3. So that's the valence shell, and the number of valence electrons we found just by looking at the group number. And on your periodic table, it'll say 5A or 15. Don't worry about the 15, just worry about the 5A. There are 2 in the S and 3 in the P for a total of 5. All right, core notation. You've already seen core notation. We worked with it. So just to make short work of it, this is the full electron configuration for iodine. So this is the full electron configuration for iodine. We're going to take the core, the noble gas core, immediately above iodine. That's going to be krypton. We put it in brackets, and then we just do whatever is left, and that's going to be 5s2, 4d10, 5p5. This portion right here. And we call this core or condensed notation in some texts. Electronic properties. We've got paramagnetism, which is the tendency of species with unpaired electrons to be attracted by an external magnetic field. Sodium metal has an unpaired electron. Anytime you have an odd number, you have an unpaired electron. Calcium +1, if you had a +1 for calcium. Any odd number of electrons is just a knockoff that you've got a paramagnetic substance. It's attracted to an externally applied magnetic field. A diamagnetic substance tends not to be attracted or to be slightly repelled by a magnetic field, and as a result of its electrons being paired. So anything that has a filled valence shell, neon, fluoride ions, xenon, calcium 2+, because remember, metals tend to give up electrons to have noble gas electron configuration will be diamagnetic. That's a tendency to be not attracted or slightly repelled even to an externally applied magnetic field.
Making liquid oxygen is pretty straightforward if you happen to have some liquid nitrogen, which I do. So what I've got here, my cylinder of oxygen, and I'm passing the oxygen through this copper coil here, which is immersed in liquid nitrogen. The oxygen has a higher boiling point than the nitrogen, so it condenses in the coil, and so by the time it comes out the other end of the tube, it's a liquid. So this has been going a while. I've nearly got a full tube, so I'm just going to. Whoa! Yep, that's pretty full. So I'll just put this down over here. Okay, yeah, so good. Half litre of liquid oxygen here. I'll just show you what it looks like. So there you go, that's liquid oxygen. The first thing you'll notice about it, I would think, is that it's actually blue, which is a bit of a surprise. Colour quite often is just a manifestation of the way that light interacts with the electrons in materials. So straight away, this is saying that there might be something a bit funny about the way the electrons are arranged in oxygen molecules. What that is actually is that there are unpaired electrons. Electrons usually like to pair up. But in oxygen, there are a couple that doesn't happen to, and we call them unpaired electrons. And there's actually another unusual property of oxygen that arises from the unpaired electrons, which I want to show you now. Right, I've got a great big magnet here, as you can see, just a couple of nuts between the poles, just to bring the poles slightly closer together. And I'm going to pour the liquid oxygen between the poles, like so. And there you go, you can see the oxygen, until it boils away, is sticking briefly between the poles of the magnet. So what's going on here, again, is because of those unpaired electrons. Electrons, in any electron in an atom or in a molecule contributes a small magnetic dipole moment. Normally when those electrons are paired up, the magnetic dipole moments cancel out, but obviously with oxygen, you have these unpaired electrons, that doesn't happen. So as a result, the whole molecule has a residual dipole and acts as a tiny little magnet. So I'll keep on pouring this in and we can keep on looking at it. Now normally when the oxygen is just sitting in the flask or in the air, all those tiny little magnets are pointing in random directions basically, so they all cancel out, so there's no net macroscopic magnetic field. But when you introduce the permanent magnet to the oxygen here, then you get those magnetic molecules all slightly aligning a bit more than they would normally, and that creates a net magnetic field. So the induced magnetic field then interacts with the magnetic field from the dirty great magnet, and you get the oxygen sticking in the poles. Now this phenomenon is something called paramagnetism, where you get an induced attractive magnetic field in a material. And I think it was actually Michael Faraday who discovered that oxygen was paramagnetic right here at the RI. So one final thing, seeing as this is liquid oxygen and this is the Royal Institution, I'm going to set something on fire. This is the classic demonstration of oxygen relighting a glowing splint.